Hello everyone, how are you? I hope you all are doing well. So today let's start with integrated rate law equation of second order reaction, where our condition that both the reactants should have different concentration. So let's start. So for example, let's take an equation at first. That is A is one reactant, it is reacting with B and giving the product P. But the condition itself says that the concentration of both the reactants should be not same, should be unequal. So let's suppose here the concentration of A is A at time 0. That means initial concentration of A is A and initial concentration of B is B. Now as the reaction is not started, then the product won't be formed, right? So here the concentration of P must be 0. Now after some time T, when the reaction starts, some amount of A and B, some amount of reactants is consumed during the course of reaction. Let's suppose X amount is consumed during the course of reaction, and from here B, X amount is again consumed. Now the product which will be formed will be equal to the amount that is consumed. So here let's suppose the product formed is X amount. Okay. Now we need to write the rate of the reaction at time T. So let's suppose write the rate of the reaction in terms of product. So we can write dP by dt. Since we are writing the rate in terms of product, here it should be positive sign. So dP by dt equals to rate constant K into concentration of A into concentration of B. Since we are writing this rate in terms at the time T, so we can write dP as X. So we can write dx by dt equals to K into A, concentration of A at time T is A minus X and concentration of B at time T is B minus X. Okay, so now on integrating, we can cross multiply each other. So here we can write 1 by A minus X into concentration of B minus X into dx equals to K into integration of dt. Now the time here the lower and upper limit will be T equals to 0 to T equals to T, and the concentration will obviously be from at time 0 the concentration will be A, and at time T we can write the upper limit accordingly we can write. Okay. So now there will be integration of parts. So we can integrate it by integration by parts. So it is basically all mathematics. Since we are dealing it in chemistry, we are not exactly going to integrate it because that's the mathematical portion, right? So we will just write the result. If you want, you can try integration on your own and just writing the result after integration by parts. So here the result will be Kt. On integrating dt, we will get Kt equals to 1 by B minus A into ln concentration of A by A minus X divided by B minus X. This is our basically the formula of second order reaction, of integrated rate law of second order reaction when the concentration of both the reactants are different. Okay, so we can apply this formula further. So let's start. So as we have discussed about the integrated rate law equation of second order reaction, where the reactants are different, having both different concentrations as well. So its application, we can use it in pseudo first order reaction. Now let's see what is this pseudo first order reaction. Okay, so basically we know that it is the application of second order reaction, right? So we will just simply write the reaction at first. Let's suppose, let's take a reactant A which is reacting with B, and the product which will be forming is P. Now let's suppose at some time T, at initial time, at time equals to 0, it have initial concentration of 1 mole and it have a concentration of 1000 mole. Now as the reaction is not started yet, so the product will be 0. Now at time T, after the reaction is proceeded, let's suppose some amount of 1 is consumed. Let's suppose 0.5 mole is consumed. So as it is consumed, I am symbolizing it with negative sign, minus 0.5. Now the product, now the reactant which will be left unreacted will be again 0.5 mole, and from here also 0.5 mole is consumed. So the unreacted part will be 999.5 mole. Okay. Now let's suppose at equilibrium, at T equilibrium, again 0.5 mole is consumed, and here hence all the reactants of A is consumed, and from there, from B again minus 0.5 molar is consumed. Then the amount which will be left unreacted will be 999.0 molar. Okay, so basically this is the reaction which is actually happening at different course of time. So let's write the rate of the reaction. Now our rate, we can write it again in terms of dP by dt, where the sign needs to be positive. So dP by dt equals to K into concentration of A into. So now before telling this, before proceeding here, I'll just tell you one story, that let's suppose I and my friend have different amounts of money we have. Let's suppose I have 10 rupees and my friend, she has 1000 rupees with her. Okay, so after some time, let's suppose I have lost 1 rupee, okay, and my friend also lost 1 rupee. So it bothers me most. Why? Because I have already a less amount, and from lesser amount also I have lost 1 rupee. So I will feel more bad. Okay, but according to my friend, since she lost only 1 rupee from the 1000 rupee, it is a smaller value in comparison to 1000. So it doesn't bothers her most. Okay, so same concept applies here itself. Since it has the very lower concentration, that is 1 molar, and from 1 molar after the reaction 0 is left. So here the change is actually visible. There is actually a we can say that the change is considerable amount of change has occurred here, but here the change is negligible. Okay, from 1000 only 1 molar has been lost. Okay, so there will be a negligible change. Okay, why? Because 999 can be approximately equal to 1000, right? So we can take this change as constant. We can consider this change as constant because it is a negligible change. Because it is a negligible change. Okay, so since it is constant, so we can modify this rate equation as dP by dt equals to K into concentration of B into concentration of A. Now since K is also constant and B is also constant, we can consider it as a new rate constant K dash with multiplied by concentration A equals to dP by dt. Okay, started with two reactants having two order, but after the reaction we can observe that the rate only depends on one reactant only, okay, where the order of the reaction is 1. So that's why this topic is named as pseudo first order reaction, because it's actually first order reaction. Two reactants is involving, but the fact is false, okay. So there is only one reactants on which the rate is depending. So that's why we name it as pseudo first order reaction. Now, as we have the formula, that is Kt equals to 1 by B minus A ln A by A minus X divided by B minus X. Okay, we can say that in comparison to B, which is 1000, the change, that is X value is very lower. Okay, so as 1000 is far greater than 0.5, we can consider that B is far greater than X. So we can consider X as negligible. On considering X as negligible, B by B will be cut out and only 1 will be left. Okay, and again 1000, let's compare 1000 with 1 molar. Okay, again we can consider that 1000 is far greater than 1. So we can conclude that B is again far greater than concentration of A. Then again A will be taken as negligible amount. So here we can write, we can modify it as K into B into T equals to ln A by A minus X. Now since K into B we have considered it as a new rate constant, that is K dash. Okay, so we can write it K dash into T equals to ln A by A minus X. Okay, so this is our new formula of pseudo first order reaction. So we can apply this formula, okay, where this K dash is rate constant of pseudo first order reaction. Let's simply write it. Rate constant of pseudo first order